So we have studied the various terms used in the Nyquist plot. Now what are the steps to plot the Nyquist plot? Let's see. The first step is to determine the transfer function GSHS of the control system. Next, step number second. Step number 2 is to put S equals to J omega in this transfer function. Okay. Now step number 3. Step number 3 is to draw the polar plot of this function Gj omega and Hj omega. How to draw the polar plot? We have already studied in our earlier videos that how we can draw the polar plot of a system. So third step is to draw polar plot of Gj omega, Hj omega. Okay. Now step number 4. Step number 4 is Nyquist plot is obtained by drawing the mirror image of this polar plot from omega when omega is varying from, that is the frequency is varying from minus infinity to infinity. So just draw the polar plot and draw its mirror image so that you will obtain the Nyquist plot. So Nyquist plot is obtained So we can say that the Nyquist plot is a special case of polar plots, and where the omega it is varying from infinity to minus infinity. Earlier in polar plots we vary the frequency from 0 to infinity. Here we are varying the frequency from infinity to minus infinity. So what we can say that Nyquist plots is a special case of polar plots in which okay, so Nyquist plot is a special case of polar plots in which the omega equals to 0 plus and omega equals to 0 minus, they are connected by an arc of infinite radius and with some specific angle. So it is a special case of polar plots. Now there is a table where we can link the polar plots and the angles and the frequency. So let's see this table. Okay, so the first part, it shows the type of GSHS, that is what is the type of our transfer function, whether it is type 0, type 1, type 2 system. And the second part, it shows the angle by which omega equals to 0 plus and omega equals to 0 minus are connected. So for type 0 system, the omega equals to 0 plus and 0 minus, they are connected by an angle 0 degrees. For type 1, they are connected by an angle minus pi. For type 2, they are connected by an angle minus 2 pi, 3, minus 3 pi. For minus 1, it is pi, and minus 2, 2 pi. So in this way, the angle by which both the frequencies they are connected, it is varying. That is for type 1, type 2, type 3 system, the angle is minus pi, minus 2 pi, minus 3 pi, and for type minus 1, minus 2, the angle is pi and 2 pi. So this table, it is used to determine the angle okay, so we can find out the angle by which these two frequencies they are connected. So it was our fourth step to draw the Nyquist plot. Now step number 5 is calculate the total number of encirclements of the point minus 1 plus j0. So total number of So step number 5 is to calculate the total number of encirclements of the point minus 1 plus j0. Okay. Now in this encirclements, the clockwise, if the encirclement is clockwise, then it is taken as negative. Encirclement means that this point minus 1 plus j0, it is lying inside that path which is crossing, which is formed by joining the polar plots. So if we because our step number 3 is to draw the polar plot. Now if the polar plot, if this point minus 1 plus j0, it is lying inside the polar plot, then the number of encirclements of this point, it is calculated, and if the encirclement is in clockwise direction, then it is taken as negative. So it is our step number 5th. Now step number 6th. Step number 6th is for a closed loop system. In step number 6, we are going to find out the stability of the system. Okay, so in step number 6, for a closed loop system to be stable, the Nyquist plot So for a closed loop system to be stable, the Nyquist plot of this transfer function GSHS, it should encircle the point -1 plus J0 as many times as the number of poles of GSHS that are lying on the right hand side of the S-plane. Because if the poles they are lying on the right hand side, that means the system is unstable. Because if the roots are lying on right hand side and having a positive real part, then they will lie on the right hand side of the S-plane and the system will be unstable. So for a closed loop system to be stable, the Nyquist plot, it should encircle the -1 plus J0 point as many times as the number of poles of GSHs that are in the right half of the S-plane. Or we can say that there is an equation through which we can check the stability, and this equation is N equals to P minus Z. Okay, here N is the number of encirclements of this point -1 plus J0. P is the number of positive poles, that is the number of poles which are lying on the right hand side of the S-plane, and Z is the number of roots of the characteristic equation. So we can also use this equation N equals to P minus Z. Let me write that what these N, P and Z are. N is the number of encirclements. Number of encirclements of the point -1 plus J0, and P, it is the number of positive poles or we can say that the poles of GSHS on the right half of the S-plane. Okay, and Z is the number of roots of the characteristic equation. With positive real part. Okay, so here we are considering only that roots or poles of this system which are lying on the right half of the S-plane. We are only consider with these poles and roots only. Okay, now when we calculate this N equals to P minus Z, then there are three cases. First case is if this Z is equals to 0, or we can say that N is equals to P. That is the number of encirclements of the point -1 plus J0. It is equal to the number of positive poles or poles of GSHS on the right half of the S-plane. So if this condition occurs that N is equals to P and Z comes out to be 0, then it indicates the closed loop stability of the system. Okay, so if Z is equals to 0, the closed loop system is stable. Now case number 2. Case number 2 is when if P is equals to 0. That is, the system is having no positive poles. All the poles are lying on the left half of the S-plane and having negative real part. Okay, so if P is equals to 0, then it indicates the open loop stability of the system. Okay, so if P is equals to 0, then open loop is stable, and if Z is equals to 0, then closed loop system is stable. Okay, now case number 3. Case number 3 is if z is equals to 0 and also p equals to 0. That is, z is also 0 and p is also 0. Then it indicates the overall stability of the system. Okay, because z is equals to 0, then closed loop system is stable. P equals to 0, then open loop system is stable. Open loop stability is there. So if both z and p are 0, then open loop and closed loop both are stable. So it indicates the overall stability of the system. Okay. So these are the 3 cases based upon that equation n equals to p minus z. So these are the steps. These 6 steps are used to plot the Nyquist plot of a system. Okay. Now, what are the advantages of this Nyquist plot? Why we use Nyquist plot to find out the stability of the system? Let's see. The first advantage of Nyquist plot is that first advantage is that most of the control systems, that is real-time system, they experience delay. Okay, so these systems, they have loop transfer function which is involving exponential terms in it. So such types of systems, they cannot be treated with, or their stability cannot be found out using the Routh-Hurwitz and the root-locus methods, because exponential terms are involved in such systems. Okay, so for finding out the stability of such systems, the Nyquist plot, they can be used. Okay, because Nyquist plot is based upon the frequency response of the system, whereas the Routh-Hurwitz and root-locus, they are based upon the time domain analysis of the system. So for the systems which are having exponential terms in their response, the Nyquist plot can be used to find out the stability of the systems. So this was the first advantage of the Nyquist plot. Second advantage is that it can be easily obtained when we are using computerized methods. Okay, using the computers, we can easily find out the Nyquist plot of a system. So second advantage is that it is easy to obtain. Now these Nyquist plots, they are used to find out the stability of the system, and stability, we know that it is of 2 types: absolute stability and relative stability. So these methods, Routh-Hurwitz, root-locus, they just gives us information about the absolute stability of the system. They don't give any information about the relative stability. So for relative stability, we can use these Nyquist plot because it gives information about both the relative and the absolute stability. So gives information about both relative Okay, now fourth advantage is that as the Nyquist plots, they are based upon the frequency response of a system. So using the Nyquist plot, we can also obtain the frequency domain specifications of the system. So fourth advantage is that it also gives information. Okay, so it also gives information on the frequency characteristics of the system, like peak resonant frequency, peak resonant amplitude, gain margin, phase margin, bandwidth. So all these specifications, frequency domain specifications, can be obtained from the Nyquist plots. So these were the advantages of the Nyquist plot. Now let us see that take some common examples of the transfer functions, and let's see that how their Nyquist plot is seen. Okay, so what is the shape of their Nyquist plot? So whenever you are going to face any question, then let's compare the transfer function with these transfer functions, and you will be able to get that what will be the shape of the Nyquist plot for such systems. So let's take some examples here. So let us see some of the important Nyquist plots of the commonly encountered transfer functions. So here we are having the serial number, and then this is the GSHS. Okay, so first we have the transfer function as k upon st plus 1. Okay, so if this type of transfer function is seen, then its Nyquist plot will be okay. So this is the imaginary axis, real axis. The polar plot, it is starting from omega equals to 0 to omega equals to infinity. Nyquist plot, it is obtained by drawing the mirror image of this polar plot. Okay, so this is the complete Nyquist plot. Now, what we can say about the stability of such system, because for this system, as P is equals to 0 and Z is equals to 0, so the system is open loop and closed loop system are stable. Okay, because the number of poles which are lying on the right hand side of the S plane and the number of poles which are having the real part as positive, they are both 0. So the open loop and closed loop both are stable. Now for second transfer function, we are having st1 plus 1 and st2 plus 1. That is, we are adding a pole. So for this, the Nyquist plot will be this is the polar plot starting from omega equals to 0 to infinity, drawing the mirror image. So it is the complete Nyquist plot. there is no encirclement of this -1 plus j0 point, so the system is P equals to 0, Z equals to 0, so both open loop and closed loop system are stable. Okay, now third transfer function. Third, we have just add another pole is T1 plus 1, is T2 plus 1, and is T3 plus 1. So such type of system will have the Nyquist plot as so this is for this system imaginary axis, real axis, this is the point -1 plus j0, so the system is unstable. Okay, fourth we have K is T2 plus 1 upon is T1 plus 1 is T1 minus 1. Okay, so we are having one pole which is lying on the right hand side. So for this we have P equals to 1 and Z equals to 0. So open loop is stable. Sorry, unstable because P is equals to 1 and closed loop is stable. Okay. Fifth, we have K upon S is T1 plus 1. That is one pole is at the origin and we have another pole. No zero is present. So for this function, the Nyquist plot will be P is equals to 0, Z equals to 0. So both open loop and closed loop are stable. If you can remember these transfer functions and their respective Nyquist plot and the stability, you can have an idea whenever you have questions to plot the Nyquist plot. You can compare the transfer functions with these transfer functions and can get an idea of about the stability of the system. Sixth, we have K by S, that is only one pole which is at the origin. So such type of systems will have the Nyquist plot as the imaginary axis. So both open loop and closed loop are stable for such type of system. Next we have K upon S is T1 plus 1 is T2 plus 1. Okay, one pole at origin and two other poles. So for this, the Nyquist plot will be so P is equals to 0, Z equals to 0. So open loop and closed loop are stable. Next transfer function, here we are having a 0 and two poles at the origin and one pole on the right hand side. So for this system, the Nyquist plot will be drawing its mirror image and then forming a semicircle. For this case also, P is equals to 0, Z equals to 0. So both open loop and closed loop are stable. Okay, so these are the 8 transfer functions for which we have seen their Nyquist plot, and we have seen that what will be the stability for these systems. So in this video we have studied about the Nyquist plot and how Nyquist plots can be used to find out the stability of the system. I hope this video is clear to you. Thank you.